So, for the rest of this lecture, we're going to be spending the time going over a math review. We're going to be talking about significant figures and vectors. If you're not very comfortable with these things, please go to my Physics 1111 lectures and watch the first couple of those. I'm going to assume that you kind of understand that, you've seen it before, it might not be completely fresh in your memory, but we'll go through it kind of quickly now, and then we'll be using them for the rest of the semester. In particular, we're going to be using vectors a lot, so it's really important that you understand how to use vectors. What do they mean? How do you describe them? How do you use them in different sorts of calculations? Things like that. So, first of all, significant figures. In physics, physics is a very quantitative subject. That means that we use a lot of numbers. We use measurements, we do all sorts of calculations with those measurements. So we're going to be using numbers a lot, and it's going to be very, very important that we understand what we mean when we use those numbers. That might seem like a silly question, a silly statement, but what do we mean when we use numbers in physics? Let's say if we make some measurement. We measure something, maybe the length of a table, or the amount of time it takes to do something, or how fast something is moving, or whatever, any kind of measurement. And we come up with some number, say 4. What do we mean by that number, 4? Well, like I said, most numbers that we'll be dealing with in physics come from some kind of physical measurement. You're making a measurement of some physical object somehow. Typically, those measurements are not going to be exact values. They're not exact quantities. Now, there are some exceptions to that, and I'll mention those as we get along, as we go along and we come across those things. But for the most part, when we say something is 4, what we really mean is that the quantity that we're talking about is about 4, or approximately 4. Well, when we say 4, what we really mean is a value that is hopefully closer to 4 than it is to 3, because if the value were really 3, hopefully we would have said 3. Likewise, hopefully the value in question is closer to 4 than it is to 5. Likewise, if it was big enough, we would have said it was 5 of something or whatever. Well, we keep track of how accurate, how precise really, these numbers are by the number of digits that we quote in our value. For example, if we wanted to say that this was really closer to 4 than just roughly 4, we might say 4.0 or 4.00. The numbers of numerals, the number of numerals that we put in the value we're talking about, are what we refer to as the number of significant digits or significant figures. I'll basically use those interchangeably. Let's take a look at how many sig figs for significant figures, a quantity has. Now, when there are no zeros in a number, like 5, 2, 6, 7, as long as there are no zeros, you can basically just count up the number of numerals in the quantity, and that tells you how many sig figs it has. For example, this has 1, 2, 3, 4, so this has 4 sig figs. I'll use SF for short for sig figs, and sig figs is already short for significant figures. So 4 sig figs. The question arises about zeros. Zeros make it a little bit more complicated. Now, there are 3 rules for counting zeros. In other words, 3 rules for determining whether a zero is significant or not. The first rule we'll call sandwiched zeros. A sandwiched zero means a zero that is in between non-zero digits. For example, 507. We'll refer to that zero as a sandwiched zero. Sandwiched zeros are always significant. So, 507, 1, 2, 3, that has 3 sig figs. And it doesn't matter if you have more than 1 zero. 5007, both of those zeros are sandwiched. Those would be both significant. 1, 2, 3, 4. That would have 4 significant figures. And likewise, it doesn't matter if there's a decimal point in there. The decimal point in this case doesn't affect whether those zeros are significant or not. So again, 1, 2, 3, 4, that would have 4 sig figs. So that's the first rule, sandwiched zeros. The second rule is zeros to the left of all of the non-zero significant figures. So what about a number like 0.0076? Zeros to the left of non-zero digits. These zeros, 7, 6, those are the non-zero digits. These zeros are to the left side of the non-zero digits. Zeros to the left of the non-zero digits are never significant. So these zeros are not significant. So we have only 2 sig figs. It doesn't matter how many zeros there are, if they're all to the left of the non-zero digits, they're not significant. So 0.000000009, how many sig figs does that have? Well, none of these zeros are significant, so only 1. If this number had been 0.0100000009, well, now those zeros are sandwiched zeros because they're in between the 1 and the 9. So how many sig figs in this case? 1, 2, 3, 4, 5, 6, 7, 8, 9. That would have 9 significant figures. Okay, so we've got rule 1, sandwiched zeros. Rule 2, zeros to the left of all of the non-zero digits. What about zeros to the right of the non-zero digits? Now this one is a little bit tricky. 5, 7, 0, 0. Are those zeros significant or not? Zeros to the right of the non-zero digits are significant only if there is a decimal point present. Now, there are different rules for this. Different people will use different ways of describing whether those zeros are significant or not. The one that I will use in our class will be that. Zeros to the right of the non-zero digits are not significant unless there is a decimal point present. So, do we have a decimal point indicated in that number? We do not. Those are not significant, so this number would only have 2 sig figs. If this number were written like this, with a decimal point, that decimal point makes those zeros significant. So that would have 1, 2, 3, 4 sig figs. And it doesn't matter where the decimal point is. It could be 0.5700. We've got a decimal point in there. That makes those significant, so that has 4 sig figs. Maybe 570.0. Doesn't matter. If there's a decimal point, they're significant, so 4 sig figs. Those are the rules that we will use for our significant figures. Okay, now, how do we use the number of significant figures when doing operations, when doing some kind of mathematical equation? Well, let's take a look. Let's imagine that we've got a problem like this, 52 times 617. So what's the answer to that? Well, if you multiply this out on your calculator, or if you do it by longhand, what you get is 32,084. So the question is, can we really quote all of those digits? Well, no, and I go through this in much more detail in my 1111 lecture on significant figures. So if you want to refer back to that, if you don't understand why we make these approximations, then you can do that. But the general rule of thumb that we will use is, when multiplying numbers, determine how many significant figures the numbers have that you are multiplying. Now in this case, 52, how many sig figs does that have? Well, that has 2 sig figs. 617, how many does that have? 1, 2, 3. It has 3 sig figs. Then your result can only keep the number of significant figures that the smallest value has of the numbers you're multiplying. So 2 is less than 3. We can only keep 2 sig figs. So we need to write 32,084 with only 2 significant figures. Well, starting from the left side, that means 3 and 2, so we write 3, 2, but we can't just write 32. Obviously, 52 times 617 is not 32. We have to put in those other zeros to fill in the places, so 32,000. Again, notice there's no decimal point, so those zeros are not significant, so that only has 2 sig figs. So we would actually just write that 52 times 617 is 32,000. We know that is not excuse me, exactly correct in terms of the mathematics of it, but in physics, that's exactly what we will write. We know that anytime we are multiplying quantities, we are going to be using the appropriate number of significant figures. Now, some people will actually have a rule that if there's no decimal point present, these numbers are assumed to be exact quantities. Exact quantities are something that you can basically assume have an infinite number of significant figures, so to speak. I'll come back to quantities like that a little bit later on. I don't want to put in extraneous decimal points just all the time to indicate a quantity is not an exact value. Exact values are something that we will rarely see rather than in the majority of the time. So I'll just assume that all numbers are written with the appropriate number of significant figures, and you just have to kind of remember which numbers really are exact values. There really aren't that many that we have to worry about, so it's not that bad. Okay, so there we go. 52 times 617 equals 32,000. And it doesn't matter how many quantities you're multiplying. We could say 52 times 617 times 1.3 times 7.8932, whatever. You just look at the number of significant figures that each value has, whichever has the smallest. And again, well, that's got 2, so we'd stay with 2. You use that number of significant figures in your answer. And the same rule applies for division. If you have some numbers like 52 times 617 divided by 3.14, whatever. I didn't really think of this as being pi, but if you have pi in there, your calculator usually assumes a much larger number of significant figures for pi, so you don't have to worry about counting up the sig figs in pi. But anyways, you count up the number of sig figs, 2, 3, 3, use the smallest number if you've got some kind of division. Okay, great. Now, what about addition? Addition and subtraction. The rule for that is a little bit different. Let's imagine we want to add these numbers. Let's say 4.37219 plus 0.012. Now, how do we add those together using the appropriate number of significant figures? Well, let's write them one above the other, just like you would in a normal way of multiplying, adding numbers. Sorry. So we've got 4.37219. We line up the decimal point, 0.012. Now, let's just add them together and think about the idea that we're using significant figures. Well, first, over in this column, remember, we're going to keep these columns in line. So 9 plus what? What is down here? What is right there? Well, we don't have anything written. So is it a 0? Well, no, we don't know what it is. It's not a 0. If that were really a 0, a significant digit of a 0, we would write 0. So we do not know what that digit is. So it's something we don't know. I put a little question mark there. What's 9 plus something we don't know? We don't know. So we don't know what goes down there. Well, what's 1 plus a blank spot? Well, again, we don't know what's down there. So 1 plus we don't know is we don't know. And then, let me get rid of these extraneous lines here. And then 2 plus 2. Oh, well, we do know what that is. 2 plus 2 is 4. 7 plus 1. Oh, we know that. 8. 3 plus 0. Now, we do know that that is 0. We do not consider that 0 as a significant digit, but we do know it is 0. So 3 plus 0 is 3. 4 plus 0, 4. So what do we get? 4.384. And there is our result. We cannot quote these digits because we don't know what they are. Now, let's notice. We've got 1, 2, 3, 4, 5, 6 significant digits for our first number. These are not significant. 1, 2, so 2 significant digits for our second number. And we end up with 4 significant digits for our final result. Well, there is really not a general rule of thumb. You might say, oh yeah, well 6 minus 2 is 4. Well, it doesn't really just always work like that. So, there's not a general rule of thumb just by counting up the significant digits. What we can do is count up the decimal places. Now, let me get rid of these lines here. I think this is making it a little bit harder to keep track of what's going on. There we go. Okay, so 7.9. What we do in this case is we count up decimal places. So, in this case, 4.37219, that has 1, 2, 3, 4, 5 decimal places. What about 0.012? That has 1, 2, 3 decimal places. We keep the smaller number of decimal places in our result. 4.384, that's got 3 decimal places. So our final result has 3 decimal places. So, for addition and subtraction, we look at the number of decimal places in our result, and we keep the smaller number of decimal places. Now, one thing I want to put a little addition here that actually goes along with multiplication too. What if you have a result that looks something like 5.2179? And let's imagine that we want to round this to 2 significant figures. Well, 5.2179, we round it to 2 sig figs, that just becomes 5.2. What if we wanted to round that to 3 significant figures? Well, here we've got 5.21, but notice that next digit is a 7. This number is actually closer to 5.22 than it is to 5.21. So, because this number is larger than 5, we're actually going to round that digit up to the next highest value. We're going to round that up to 5.22. When rounding a number to a certain number of places, certain number of significant figures, look to the next value. If that value is a 5 or larger, we're going to round up. So that 7 is a 5 or larger. It's larger than 5. So to round this to 3 significant figures, we'll round that up to 5.22 rather than just dropping at 5.21. If the digit is 4 or lower, so 0, 1, 2, 3, 4, we'll just drop it. So a 1 is smaller, it's 0, 1, 2, 3, 4. So if we were going to round this to 2 significant figures, we just drop that and it becomes 5.22. Some people say that if it is exactly a 5, so for example, let's imagine this number were 5.215 and we wanted to round that to 3 sig figs. Some people use the rule, well, if the value is a 5, then rather than always going up, they'll say, well, we'll round this to an even digit or an odd digit or something. Just always even or odd so that you're not always going upwards or always going downwards or something like that. So they would say round that to 5.22 if you were going to round it to an even number, or 5.21 if you were always rounding it to an odd number. I don't like that. The idea is, well, that number is exactly halfway in between 5.21 and 5.22. Why would you always go one way or the other? Well, my argument is that, yes, it is halfway, exactly halfway, in between 5.21 and 5.22, if all of these other values really were zeros. But if any of those digits were anything other than a 0, then that number really is closer to the larger number. So I will always use the rounding rule that 5s always round the next digit up, because it is, essentially completely unlikely, completely impossible that if this really were from some kind of measurement, that all of those would exactly be zeros. So this really should be larger, closer to the larger value. So I will just use the rule that 5s always round up, and so we would call that 5.22 if we were to round it to 3 sig figs in that case. Okay, so always keep an eye out when you're when you're rounding a number. Look at that next digit. So in this case, when you're adding numbers, let's imagine that we actually had a value over here. Let's say that were a 1. And we might say this was a 2 then. 1 plus 1 is 2. Well, notice in this case, even if we don't know what this digit is, we know it's at least going to be a 9. And so in this case, really, according to the way we're thinking about this, we would round that up to a 3. So we would actually quote this as 4.3843, rounding that up to the next highest value. So with addition and subtraction, what you can do is go ahead and add or subtract all the columns, but then look at what column do you need to keep so that you'll have that next digit to determine whether you need to round up or round down. Okay? So kind of a general rule of thumb for addition and subtraction. Excuse me. All right, now, I haven't been lecturing for quite a while, so this is my first time talking so long, so I do apologize. I've got I'm going to be coughing a little bit just because I haven't talked for so much. Now, one more thing. In this course, we're going to be dealing with many very large numbers and very small numbers. Now, there is a way of writing large numbers and small numbers that make them a little bit easier to deal with, and that form is called scientific notation. So, let's take a look at that.